Hello and welcome to this manufacturing systems technology module 21. Just quick recap of what we did in the last class. We were talking about a certain example where case study where we are talking about turning about 500 units of shaft within a manufacturing process with the design specifications of 1 plus minus 0.003 inches. We had 3 processes among which selections had to be made. Was the turret lathe, engine lathe and automatic screw machine, and this manufacturer of all the 3 machines had provided us with the data in terms of the standard deviation, the processing cost per unit, processing time per unit, setup time, and then we were supposed to do a process capability analysis of all these 3 machines and see what is the scrap fraction which would be generated. For that we calculated the scrap coefficient from the normal distribution and the design tolerance, and this came out as just done in the last lecture to be 67%. Okay. So it was 0.6779. We also calculated the technological coefficient for the scrap as 2.1048. The technological coefficient for the input is 1 plus the technological coefficient of scrap, so 3.1048. So obviously the number of units which are scrapped now they come out as the case times of y0, where y0 is the output. We have already mentioned that the case is about 500 units of turning of shafts. So this comes out to be 3.1048 times 500 is about 2.1048 times of 500 which is recorded as 1052.4 units. So these are the number of units which are scrapped by the process, and the total amount, total raw material inputs units would come out to be equal to the technological coefficient for the input times of the 500 output capacity. So this can be recorded as 1552.4 units. So you can see that just by a certain process selection for the first case, which is the turret lathe, you are having a scrap value or scrap quantity which is almost double the number of the input which has been planned. So therefore in order to make a 500 unit output, you have to scrap about 1000 plus parts in the particular system if you were to make the choice of a turret lathe. We will have to again go along and try to investigate all 3 in comparative capacities and then finally take a decision whether turret lathe should be scrapped at this stage or not. But what you will find out is that based on the various capabilities, if the capability of a machine is higher, obviously the cost is going to be higher as well of the particular machine, okay, and so also of the operation cost, the overall operation cost of the system. But on the other hand, if the cost of the machine is lower and the capability is not so good, you basically lose in terms of scrap materials from the process. So there is a sort of trade off which needs to be made between these 2 aspects when we are doing a selection or a choice. So the manufacturing lead time in this particular case can be represented by the setup time plus processing time per unit value. In case of turret lathe, it is recorded as 1.0 .00 minutes per unit, and the setup time is recorded as about 15 minutes. Okay. So the total manufacturing lead time will then be, in terms of the setup time plus the input quantities which has been borrowed from this expression earlier, times of the time processing time needed per input or per raw material input to the manufacturing system. And so this would come out to be, in this case of turret lathe, equal to 15 plus 1.00 times of 1552.4 units, that is about close to 1567.4 minutes. So that is how big this is going to be time wise in terms of 1567.4 minutes, that is the manufacturing lead time. And the unit output cost x0 then comes out to be equal to Ki xi minus Ks xs plus Ki, the technological coefficient for the input, times of the processing cost at the input level yi. This is borrowed from derivation done in the earlier modules. In this case the Ki value comes out to be 3.1048 times of the xi, which is actually the cost of the input raw material. So if we look back here, the cost of the input raw material, the unit cost comes out to be about $10 per unit, and so the salvage cost again xs comes out to be equal to $2. This is xi, this is xs, and based on these, and the processing cost again per unit for the turret lathe comes out to be $7 a unit. Okay. So that is how distribution is laid, and we have 3.1048 Ki times of xi, which in this case is about $10 a unit, minus of the Ks, which was 2.1048 times of the unit salvage cost, which in this case is about $2 again, plus the technological coefficient of the input times of the processing cost, which is again in this case about $7, I just pointed out. So this brings us to an output cost level XO of about $48.572. Okay. So that is per unit cost, the per unit output cost in this particular case. So we have several things now derived to take a management decision, particularly for the turret lathe case. We talk about the number of scrap units, we talk about the total input requirement, we also talk about the lead time, manufacturing time for processing this whole 1552 units of raw material, and then finally also talk about the unit output cost which comes out from all this process. And if we just try to summarize for the all the three systems, so we have a summary table here. Let me just write it down. So you have type of machine tools, and there are three type of machine tools that we are trying to consider for this process selection decision. One is a turret lathe, okay. Another is engine lathe, and the third is an automatic screw machine. So obviously the unit cost is $48.57 a unit, $21.28 a unit, $25.03 a unit. Similarly the scrap in terms of number of units in all the three categories happen to be 1052 units in case of the turret lathe, goes down to 33 and 1 unit in case of the engine and the automatic screw machine. One of the reasons why probably they are costlier is their capability is immense in comparison to the turret lathe. It is very gross, the turret lathe thing. And then of course you also have the manufacturing lead times that you have calculated, and this manufacturing lead time comes out to be 1567.40, 510.06, 410.70, and then you have to take a manufacturing decision here. So obviously if the business environment was something which would be going by minimum lead times, then you will choose let us say we call it option 1, 2 and 3. So if the business environment is determined by minimum lead times, there are situations where you have this kind of business environment. So then obviously option 3 is the best option, and if the environment is cost competitive, then 2 can be the right option. So if you are planning to buy cost wise and see minimum cost, engine lathe comes out to be the right option, and if it is a lead time based demand from the environment, that the one who will be having the minimum lead time has to be considered for this particular process, you will have to choose the automatic screw machine for that purpose. So that is how you actually take a decision criteria for the CAP process at the stage of machine selection, so that you can choose a particular machine for a process. So you already saw how we chose a machine for a turning process in this particular zone. So I am going to sort of go ahead and go to the next section, which is about determining machining conditions, that is cutting speed, feed, depth of cut, manufacturing times like let us say setup time, processing time and lead time, etc. The idea here again is that as far as possible we want to complete all these steps in a single go, so that in a very intelligent manner not only you are able to decide what is the sequence, what is the operation itself, but their sequences and also the right kind of machines, tools, working holding devices and the machining conditions, so that you have a complete optima in terms of the manufacturing process. So for doing that, how to determine the machining conditions, now we will have to do this, we have to first specify the working material. Okay. So specify the workpiece material and the machine tool and the cutting tool, and the question is what can be controlled to reduce the cost and the increased production rate. Obviously the controllable variables here are the cutting speed, the feed, the depth of cut, and jointly the VF and D, all the 3 parameters are referred to as machining conditions. Okay. So there are a number of models specifying optimal machining conditions, and out of which the best ones are the minimum cost model. Okay. So you have one model where you have to really consider the minimum cost per piece, and another criterion that is used, the model 2 for the optimal conditions, is the maximum production rate model, where you talk about minimum lead time, manufacturing lead time. So these are the 2 criticalities in terms of any manufacturing system. One is the cost and another is the lead time, as you also saw in the process capability analysis based selection done in the earlier case study or the problem example. So let us now focus a little bit about what really is meant by this minimum cost per piece of a certain machining situation or condition. So the average cost per piece to produce a workpiece can be a combination of several costs coming from different, in a particular machining situation, several different costs coming from different aspects. So let us look at some of the costs which can really bother us while we are talking about machining. So let us look at towards this side of the slide here, right here. So there can be a cost rate which includes labor and overhead costs. Okay, there can be a tool cost per cutting edge, which depends on the type of the tool that has been used. There also can be based on these the different timings. For example, there can be a non-productive time. So this is actually per minute. As you see, all the costs are time driven, so we have to have a time domain also, so that we have overall cost. So one of them could be non-productive time, consisting of loading and unloading the part to the machine. Okay, there can also be the actual machining time per piece in minutes per piece, and obviously something needs to be done with the tool life, because when we are talking about the tool and the quantum of or the number of minutes that a tool would have to wear down. So obviously after that wear down, the changeover would be needed, and so therefore the time to change a cutting edge would be also critical. Okay, and also the actual cutting time per piece, which is approximately equal to TC, but sometimes there may be other factors which may lead to this TAC being different than the TC. Okay, so as of now we can say that it is approximately equal to the cutting time, and we are assuming that some of the wait periods before the coolant starts or coolant stops or something like that is not considered in the differentiating the TC from the TAC at this particular process step. So what are the parameters which are to be optimized? Obviously the cutting speed in meters per minute needs to be optimized, the feed rate needs to be optimized, the depth of cut needs to be optimized. We know there is an exponential n which is related to the tool life equation, the Taylor's equation, so on and so forth. So we have given all these constraints now, right. So the average cost per piece to produce a work piece, if we split it up into the different costs with sum out to be the average cost, let us say the cost per component we call this CU in this particular case, it is unknown cost. Okay, it will be broken down into the non-productive cost per piece plus the machining time cost per piece we can also call it the productive time, plus again the tool changing cost per piece plus the tooling as such. So the tooling cost per piece. So that is how you define the average cost to produce a workpiece. And if I really look at some of these parameters that I have illustrated on the right here and some in the lower portion of the slide right here, we can first do something about the tool life, so that we have an idea of how frequently we need the tool changing or those issues. So obviously the tool life equation is a standard format of the Taylor equation Vt to the power n equal to C, which is the constant, and n of course is the index which we are talking about in this particular case. So the overall cost per piece then would be in terms of the total overhead cost, which includes labor and overheads both, CO times of the time which is the non-productive time. Okay, so this cost goes in whenever there is some kind of a decision regarding a productions to be started. So obviously these are the additional bundled costs which come into picture, plus the labor overhead which is there times the actual time of machining TC, which would be the productive cost which is added to the system now. Obviously there is a tool changing cost which is there. So the tool changing cost in this case would be really dependent on what is the actual time of cutting for the particular tool vis-a-vis the tool life. So let us say if capital T were the tool life and TAC as in this case is the actual cutting tool, we can say the number of times the tool needs to be replaced is really, in a particular actual cutting time per piece, we can get TAC by capital T replacements, so this is the frequency of replacement. And this can be bundled up with then the time actually to cut the tool. So much time is now needed to cut to change the tool, change the cutting edge. So this is the frequency, number of times the time per tool makes the overall time of cutting edge changing or tool changing, and during that time the cost rate of the labor again is assumed to be C0. And then there is a bundling of the tooling cost which comes because of such changes. So you have the total overall again cost as the number of times that you need to change a tool while one cutting cycle is on times of the tool cost per cutting edge. Okay, so these are the number of edges that you would need times of C1, the per cutting edge. So that comes out to be the overall cost per piece, and we have to do something by varying these parameters like the VF and D parameters in the cutting condition, so that you can optimize the cost per workpiece of the particular sample. So we come to the end of this module, but in the next module we are going to sort of try and see how we can do this optimization or minimization, and what is the emergence of a particular velocity, cutting velocity that will come out given that particular optimum condition. Thank you.